Welcome to today's deep dive. We are really thrilled to have you here with us.
Yeah, absolutely. We've got a great one today.
We do. Today we are exploring a pretty fascinating research paper out of Princeton University. It's titled SWE-agent, Agent Computer Interfaces Enable Automated Software Engineering.
It's quite a mouthful, but the core concept is brilliant.
Right. The core mission of our deep dive today is to basically rethink how we interact with machines. Or I guess more accurately, how machines interact with machines.
Exactly, because, we're all super familiar with how standard user interfaces cater to us, to human visual processing.
Windows, Mac OS, mobile apps, right.
Right. But we are quickly entering an era where large language models, or LLMs, are doing the driving. So the big question is, what happens when an AI needs to operate a computer autonomously?
And that's exactly what this paper tackles, because language models represent this entirely brand new category of end users. They don't have eyes.
No, they don't.
They don't need graphical interfaces. They don't need buttons or visual hierarchies or, syntax highlighting.
Which is why the Princeton researchers argue that AI needs an ACI, an agent computer interface. And setting the stage here, designing this interface layer correctly, is pretty much the critical bottleneck right now for the future of automated work.
Especially in highly complex domains like software engineering. And just to hook you right out of the gate, by building this custom ACI, the researchers allowed an AI to achieve state-of-the-art performance on major software engineering benchmarks.
Completely crushing previous methods.
Just blowing them out of the water. Okay, let's unpack this. Before we get to the actual mechanics of this shiny new interface, we really need to establish the baseline.
The before picture.
Right. When researchers first attempted to get an AI to resolve GitHub issues, they naturally just tried dropping it directly into a standard Linux shell.
A text-based computer terminal.
Exactly. And now, dropping an AI into a raw terminal environment introduces massive friction. A human engineer uses sophisticated tools like VS Code alongside a terminal to do complex tasks. But current interactive environments are built on assumptions about human cognition that just do not apply to a language model.
And the paper details exactly why a standard Linux shell is basically a terrible, profoundly hostile environment for an AI. It looks at the disparities in how humans and models process information.
Which is fascinating.
It really is. I mean, humans have this incredible capacity for visual filtering. If your terminal spits out a massive log file on the screen, your eyes naturally filter it.
You just scan right past the junk.
Exactly. You subconsciously ignore the noise and dart straight to the one error code or timestamp that actually matters. But for an AI, there is no subconscious filtering.
Everything has a cost.
Right. Every single character, every space, every line of that log file has a fixed cost in memory and computation. It eats up what we call their context window.
And that context window constraint is everything. It's the AI's working memory. So think about it like this. Dropping an AI into a raw shell and having it execute a standard command like cat, which basically just dumps the entire contents of a massive file directly onto the screen.
It dumps it straight into the prompt history.
Right. It's essentially like trying to read a complex technical book by having someone shout the entire text at you all at once without pausing for breath.
That is a perfect analogy.
It completely floods their working memory. It pushes the initial system instructions and the actual bug report right out of their immediate attention, causing them to literally forget what they were doing.
What's fascinating here is that the researchers found this penalty applies even to tools that we instinctively think of as helpful.
Like search tools?
Yeah, exactly. They tested giving the language models standard, human-like iterative search tools. Think of how you might use a basic find function on a web page, where you hit next over and over to look through the results.
Just paging through one by one.
Right. And the researchers discovered that giving the AI this standard search tool made it perform demonstrably worse than having no search tool at all.
Which seems so counterintuitive at first glance. If it needs to find a specific variable in a massive repository, how does a search tool make it worse?
Because it falls into that context window trap we just talked about. When the AI gets a large number of search results, it lacks the human intuition to stop and say, wait, I need to refine my query.
It just blindly powers through.
It gets stuck in these endless loops of just hitting next, next, next to inspect every single match. And because every single action and output consumes their token budget, getting stuck in this search loop literally exhausts its context window on irrelevant lines of code.
So by the time it actually finds the variable, its memory is so colluded with the previous 50 irrelevant results that it completely loses the plot of the actual bug it was trying to fix. Which brings us perfectly to the solution they developed, SWE-agent. The researchers realized they had to stop treating the AI like a human developer. They designed this custom ACI around 4 core principles. So let's break those down for you.
Let's do it.
Principle 1 is simple actions, and principle 2 is making those actions compact and efficient.
Right, because in a typical bash environment, you have commands with dozens of complex flags and options. It's tricky even for humans.
Super tricky. Instead of forcing the AI to memorize and perfectly format all that complex bash syntax, SWE-agent provides consolidated, streamlined actions.
And the best example of this is how the agent edits code. In a normal terminal, editing a specific block of a file without a visual interface is incredibly brittle. A human might use a utility like sed for string replacement, but that requires writing flawless regular expressions.
And if you've ever written a regex, you know how easily that goes wrong. Oh, absolutely. If an AI writes a regex that is even slightly off, it might overwrite the wrong function entirely. The alternative is having the AI output the entire rewritten file from top to bottom, which burns a massive amount of tokens.
And increases the chance of it just hallucinating a brand new error somewhere else.
Exactly. So SWE-agent throws all that legacy terminal logic out the window. It provides the ACI with a single, highly optimized edit command.
And the mechanics of this edit command are so clean. The AI doesn't navigate a blinking cursor. It simply provides 3 parameters: a start line number, an end line number, and the replacement text.
That's it.
It's a clean, single-step process. It replaces all the lines between the start and end in one atomic step. It's compact and minimizes token generation.
Which leads directly into principle 3, which is informative but concise feedback.
Right.
If the AI executes that edit, it needs immediate verification. So SWE-agent implements a custom file viewer tool. Instead of dumping the whole file like that cat command we talked about earlier, it acts as a sliding window.
It shows a maximum of 100 lines at a time, right? Yes, exactly 100 lines. And it explicitly tells the AI exactly where it is in the document. But the truly clever architectural shift in this principle is the context management system.
I love this part of the paper. Because an AI processes the entire context window at once, a long history of past terminal outputs just becomes mathematical noise. To solve this, the ACI only keeps the last 5 observations in the AI's memory.
A rolling buffer.
Yes. If an observation is older than those last 5 turns, the ACI automatically collapses it into a single summary line. It basically tells the model, you executed this command, but the verbose output has been hidden to keep you focused on the present.
It completely mitigates that shouting the whole book problem.
And they applied this same strict feedback rule to searching as well. If the AI uses the search file or search directory commands, the ACI artificially caps the results at 50.
No more endless loops of hitting next.
Exactly. If the search returns thousands of lines, the interface doesn't paginate them. It just tells the AI it found too many results and forces it to refine the query. It prevents the AI from getting overwhelmed.
It provides that necessary friction.
Now, let's transition to the most relatable part of coding, which is making incredibly stupid typos. Here's where it gets really interesting.
My favorite part.
Principle 4 is entirely dedicated to guardrails. Guardrails that mitigate error propagation.
Because language models, just like human engineers, make trivial formatting mistakes all the time. They miss a closing parenthesis, or they mess up the indentation.
Especially in Python.
Oh, yeah. And in a standard raw terminal environment, if you submit an edit with an indentation error, the terminal might just silently accept it. It breaks the underlying code, but you don't find out until much later when you run the test suite and get hit with a confusing, cascading wall of errors.
Errors that have absolutely nothing to do with the actual logic of the bug you were trying to fix.
Exactly. But SWE-agent intercepts that entirely with a built-in code linter.
If the AI tries to submit a piece of code that contains a syntax error, like an E9999 indentation error, the ACI instantly blocks the edit from writing to the file.
It stops it cold.
It shows the AI the original code, it shows the broken code it just tried to make, and it explicitly halts the process, telling it to fix the command and try again.
And the statistics from the paper prove why this matters so much. Usually the AI has a 90.5% chance of successfully making an edit right out of the gate.
That's really high.
It is. But if it makes just one failed edit in a raw environment without those guardrails, its chances of recovering and eventually fixing the bug plummet to 57.2%.
It just enters a complete downward spiral.
It really does. It tries to fix the typo with another typo, gets confused by the tracebacks, and exhausts its context window. The guardrails stop that downward spiral immediately by refusing to let the bad syntax into the environment in the first place.
So if you're listening to this, you understand the architecture now. We have these 4 principles, the optimized interface, but what does it actually look like when this AI goes to work? We want to walk you through a typical successful SWE-agent trajectory based on the researchers' observations.
Right. They identified a very consistent zoom in behavior.
How does that start?
The agent almost always initiates the run with either reproduction or localization. For reproduction, it creates a test file to run the bug and see it happen. Or for localization, it does a broad directory search to map out where the files live.
It does the broad detective work first.
Then it zooms in, moving to specific file searches and finally using a go-to command to jump to the exact lines of code.
And it's really notable that the researchers found that right around turn 5, the AI settles into a very tight rhythm. It falls into an edit then execute loop. Edit the code, run the test, edit again, run again.
And this methodology yields some truly impressive results. When they powered SWE-agent with GPT-4 Turbo, it successfully solved 12.47% of the 2,294 SWE bench test tasks.
Now, to give you some context, 12.47% might sound low if you don't know what SW bench is. These are real historical bugs scraped from massive enterprise repositories like Django. The previous absolute best non-interactive method only solved 3.8% of these tasks.
So this interface alone more than tripled the success rate on highly complex engineering tasks.
Just crushed it.
And on the human evil fix benchmark, which is simpler debugging tasks, it hit a massive 87.7% success rate.
But the financial detail they shared is probably the most fascinating part of this entire paper. They gave the AI a strict $4 budget per task.
Constrained by the cost of the API tokens.
Right, and they found that successful bug fixes were surprisingly fast and incredibly cheap. A successful run took a median of just 12 steps and cost $1.21.
$1.21 to resolve a real-world enterprise bug.
It's wild. But the flip side is unsuccessful runs dragged on for an average of 21 steps and cost $2.52.
It reveals a stark behavioral truth about current generation models. Language models succeed quickly, or they fail slowly.
They churn through their token budget until they time out, which brings up the ultimate question. Why do they fail when they do?
The audit on the failures is super revealing. 52% of the time, the AI just comes up with an incorrect or overly specific logical implementation. Another 23.4% of the time, it gets trapped in cascading edit failures.
Even with the guardrails.
Even with them, yes. But if we connect this to the bigger picture, this is actually a massive victory.
A 52% failure rate is a victory.
Yes. Because it proves the AI isn't failing because it can't operate the computer anymore. It's failing on the core reasoning logic of the code itself. The ACI is successfully getting the interface out of the AI's way.
That makes total sense. We were basically giving a supercomputer a broken keyboard and wondering why it couldn't type.
Precisely. The intelligence was there, it just needed the appropriate steering mechanism.
So what does this all mean for you listening? It means we have spent the last few years trying to force incredibly advanced AI to use tools built explicitly for human brains and human eyes. By stepping back and engineering an ACI that respects how an AI actually thinks.
Its context window, its token economy.
Exactly. Acknowledging its need for concise feedback and its vulnerability to silent errors. By doing that, we unlock massive leaps in capability without even changing a single weight in the underlying AI model.
It really highlights how constrained we are by our own perspective. And it leaves us with a final, I think, really provocative thought to consider.
Let's hear it.
This paper built an interface layer on top of a standard Linux system. It translates AI actions into human-computer actions. But as AI agents become the primary workers in certain digital domains, it raises an important question. What happens when we stop building operating systems for humans altogether?
Oh, wow.
What happens when we design the entire computer architecture from the ground up, natively, for the language model?
That is a wild thought to end on. Interacting with infrastructure that looks totally incomprehensible to us, but operates at blinding speed for an AI. Thank you so much for joining us on this deep dive. Next time you open an application, take a second to observe the software you use today and imagine how it would look if it were designed for an AI instead of you.